This is lecture 12, Brownian motion wrap-up. So as the title suggests, this is the last lecture on the Brownian motion. We're going to pick up where we last left off, which is optional stopping and martingales. So these definitions should be familiar. We're going to need to check two conditions for something to be a martingale. One is the absolute value at every single time t better have a finite expectation. And the second condition has to do with predicting where the martingale will be, given that we've observed it up to time s. We want to predict it at time t in the future, and that prediction is always going to be wherever you last saw the martingale. That's the best prediction. So in other words, the martingale stays level. It stays at the same value where it was last seen in expectation. We saw a number of examples. The Brownian motion was a martingale. The Brownian motion squared minus t was a martingale. There is another example in your homework. Another concept that we've seen were hitting times. Here I'm going to define them a little bit more generally, but a hitting time tau a, this is the hitting time of a set A and by a process M. So this doesn't have to be a martingale necessarily, just a hitting time of a process. And this is defined to be the very first moment at which M enters that set. So here's an example where the process is going to be the Brownian motion, and the set is going to be everything above 2 together with everything below minus 1. That's what this set is defining there. So the picture below me is in fact illustrating this. The complement of the set A here is everything between minus 1 and 2, and the set A is everything above 2 together with everything below minus 1. So hitting times are often called stopping times. There's a lot to say here, but what I really want to introduce is this notion of a stop process. So first of all, there's a little bit of notation, which we've seen before. So this is t wedge tau. So wedge just means take the minimum of two numbers. And now what we can do is define what's called a stop process. In this example, mt is going to be the same Brownian motion, but now I'm going to substitute a minimum with the hitting time right in there. So what does this look like? The picture below me shows two curves. So one of them is the Brownian motion and the other one is the stopped Brownian motion. And it's stopped at the hitting time of the set that has a boundary at minus 1 and 2. So in this example, the Brownian motion and the stop process are exactly the same in the beginning as they should be. And as soon as the Brownian motion hits the set A, so in here in this picture, it hits the level minus 1 first, the stop process just continues at a constant or stopped value. And the Brownian motion just goes on to do what it does. There's a bunch of more examples. So top left, again, we hit the minus 1 boundary. The red curve, which is the stop process, keeps going flat at the value minus 1 forever. And the Brownian motion does what it does. Top right, we again hit minus 1. Stop process stops, and the Brownian motion continues. In the bottom left picture, at least in this case, by time 1, we haven't hit either boundary. And so the Brownian motion and the stop process are one and the same, at least on the time interval from 0 to 1. And then finally, bottom right, you see that the Brownian motion actually hits the value 2. Once it hits, the stop process will stay at 2, and the Brownian motion will again go on to do what it does. So now we're at the point of stating the optional stopping theorem, which we've also seen. This identity here you can get very easily from property 2 by taking the expectation of both sides. And what it's saying is that wherever the martingale starts, that's where it's expected to be at any time t in the future. And the only thing that the optional stopping theorem adds to this is that this will continue to be the case for a hitting time, so for a random time. And that turns out to be pretty useful. I'll run through a number of problems that show why it's useful for a number of calculations. One caveat that I discussed last time is that you need some conditions for this to actually be true. So these are the things you verify. The first condition, and it's one or the either. You don't have to show both. The first condition I discussed last lecture, it's a little bit restrictive though. You know, the hitting time has to be bounded, so it has to happen before some time c, and you have to show that, and that's typically going to be either difficult or just not true. The other condition is a bit more involved, but it is much more broad in kind of what you know, what problems will fit this. So this is kind of a much more general way to guarantee this statement that I'm underlining. So let's kind of look at it briefly. I'll run through a number of problems and try to kind of demonstrate how to show these conditions. So in this one, the more general one, what you need is first a random variable with a finite expectation, and then you need to take the stop process and bound its absolute value, in fact, above by this random variable. So that it's sometimes simple, sometimes not. We'll see how it plays out on examples, but the second condition is generally going to be much easier to verify than the first one. The first one is, in fact, pretty restrictive. So we're going to look at some examples. This is called the escape problem, and it picks up exactly where we started with the previous example, where you have two boundaries, -1 and +2. You have a Brownian motion, which is your martingale, and you're asking what is the expected value of the time at which the Brownian motion hits either -1 or 2. So it's an escape problem because you have two boundaries and you're waiting for the Brownian motion to kind of cross or escape one or the other. And in this case, you can see that the Brownian motion in this picture, the one on the slide, it doesn't escape by time 1. And the question we're asking, well, what's the expected time of escape? So all of these follow kind of the same basic pattern, and I'll try to run through you know, how this works. So the first thing you need is a martingale. You kind of get good as to picking which one, you know, once you get enough practice. But in the beginning, you just, you know, you pick a bunch of them, and hopefully, you know, something strikes. So, and that's exactly what we're going to do. We're going to try the most obvious choice. Let's pick the martingale to be the Brownian motion itself. We know the Brownian motion is a martingale, so let's set that to be our m. The next step is to try to understand what is the value of that martingale at the hitting time, right? So what is w at time tau, right? Time tau is the very first moment we hit either -1 or +1. So not surprisingly, those are the two possible values. Either w tau is -1 or it's +2. And that's obviously going to happen with some probabilities. And those are, you know, mutually exclusive. It's one or the other. So one will have some probability p. We don't know what that is, but we can just give it a name, p. And 1 minus p, that's the complement. So let's say that the Brownian motion first hits -1 with probability p, and it's going to hit 2 with probability 1 minus p. There's one little problem here, is that nowhere in this is the time tau actually popping up. So I said in the beginning that we really want to involve the time tau somewhere, and given the martingale that we've picked, we don't really see tau anywhere. So we can try this other martingale, and you just kind of keep trying until you get what you want. So let's keep going. This one at time tau is going to be either 1 minus tau or 4 minus tau. How do I know this? Because -1 squared, that gives me the 1, and the minus tau comes from this t here. The 2 will give me 4, and again minus tau obtained from the t. So those are the two possible values, and again, they happen with the same exact probabilities. Whenever w was at -1, that happened with probability p. Therefore, m tau is going to be 1 minus tau with probability p, and 4 minus tau with probability 1 minus p. So what is this bias? There's a lot of talk and few results so far. Well, we're going to try to apply optional stopping and worry about the conditions later, which is what usually one does. So, let's plug in what we have so far into this statement. What do we get for the first case? So this is the case where m was chosen to be just the Brownian motion. The Brownian motion at time 0 is 0. That's what we get for one side. On the other side, we're going to try to expand this expectation, which is kind of a coin flip, or a biased coin flip, perhaps. So with probability p, we get -1, and that's responsible for this term. With probability 1 minus p, we get the value 2, and that's responsible for this term. So that's evaluating this expectation here. And now from this equation, you can immediately solve for the probability, and it tends to make sense. Which boundary are we more likely to hit? Is it -1 or 2? Well, -1 is closer, so it seems like we're more likely to hit it. And there's some symmetry in this, that the kind of like the total distance between -1 and 2 is 3, and so the longer the distance, the less likely you are to hit it. So in this case, you have kind of the symmetry. It's 2/3 to hit -1 and 1/3 to hit the value 2. In any case, so far, it seems reasonable. We have an expression for the probability that was previously unknown, and that came from the first martingale. Let's apply optional stopping to the second martingale, namely this one. So what do we get? If we plug everything into the right-hand side of the expression, what's m at 0? It's 0. So that explains this side. And now we need to evaluate the expectation on the left, namely this expectation here. So with probability p, we have the value 1 minus tau. With probability 1 minus p, we have 4 minus tau. So that's these two events described right here. Right, both happening with probability p and 1 minus p. And then I simplify. So p times minus tau plus 1 minus p minus tau, that gives me the tau. The p's cancel. The p's don't cancel on the constants. So we pick up a p here, and we pick up a 4 minus 3p from this term here. In the end, all of this simplifies to 2 minus the expected value of tau is equal to 0. And the obvious conclusion is that the expected time at which the Brownian motion escapes, meaning either hits -1 or 2, is 2. And what you could do is try to actually verify this with maybe some numerical experiments. So you can try to just to kind of simulate the Brownian motion and wait until it hits one boundary or the other, and write down what time each one of these simulations gives, and then average. So it kind of look like this. You just keep simulating the Brownian motion. Here it didn't. I'm going only up to time 1. You would actually have to go up to time tau and record that, and then average a bunch of these. So this would be like a Monte Carlo simulation. You can see most paths don't actually exit the boundary by time 1. And that's, gives a little bit of evidence for the answer we obtained. The answer we got was we're expected to exit at time 2, and here I'm showing various simulations up to time 1. And so here it actually exited even before time is 0.6 or even 0.5. But most of the time you see that it doesn't leave those boundaries by time 1. So here's another one where it caught -1, and so on. So you can try to implement a simulation. I'll give this code in a future slide and then see whether you can verify that answer. So how much do we trust this? We trust it to the extent that we can verify the conditions of optimal optimal stopping, and there were 2 of them. It's pretty clear that this one, the one that looks at whether the time is bounded, it's going to be tough, right? Why? I mean, do we have a reason to expect that the time at which the Brownian motion escapes is bounded? Probably not. There's no clear reason why there should exist some time before which this has to happen. And so the second condition is a little bit more flexible. In fact, it leads to a pretty simple verification. So the question is about trying to find a random variable, and that could even be a constant. So here I wrote random variable, but constant number is also a quote-unquote random variable, a degenerate one. And it obviously has a finite expectation. So any constant will have a finite expectation. It's just the value of the constant itself. And so let's think about why this is true. Why is the stop process always less than or equal to 2 in expectation? Well, that's simply because the stop process will assume the value of the boundary and just continue with that value forever. And so, either m t wedge tau is between -1 and 2, or even if it hits those values, it just remains at those values forever. And so the absolute value is bounded by 2. So in this verification step, the choice of the random variable c is just going to be the number 2. And that justifies the result. So here's a little bit of code to simulate these paths. You can see it's not too difficult, although a little bit tedious to kind of write down where exactly the process stopped. In any case, I'm gonna, in the next segment, run through many more problems from your textbook. They're all gonna have the same flavor, and let's do that in the next clip.